At the very center of the agentic architecture for software are large language models, or LLMs. It is crucial to have an understanding and an intuition about what LLMs are and what their capabilities are. In order to form that understanding, we first need to look at what an LLM actually is at its core, and how it has become such an important component of modern AI. Let's begin. To understand LLMs, it is important to recognize that at their core, they are neural networks. So we need a basic understanding of what a neural network actually is. A neural network is built from interconnected nodes, often called artificial neurons. Each of these nodes can maintain weights in relation to the next nodes they are connected to. Each of these weights can be referred to as a parameter, and the network learns by adjusting these parameters. These neurons are arranged in layers: an input layer, one or more hidden layers, and an output layer. Information moves from layer to layer, and the final output is determined by how all the inputs are combined and transformed across the network. These dynamic parameters between nodes allow a neural network to form abstractions, to learn patterns, relationships, and structure within data. This structure is the foundation of modern LLMs and what gives them the ability to abstract information. Neural networks in their initial forms were mostly a mathematical invention. But the fact that they were inspired by the structure and role of neurons in the brain always made them uniquely aspirational. And when we look at the brain, we see something remarkable. It is not a rule-based machine. It is an abstraction machine. The brain takes in signals from the world, forms internal representations, learns patterns, and makes sense of experience, even when information is incomplete, uncertain, or noisy. This ability to extract meaning and structure from raw data is what makes intelligence possible. And the idea that a network of simple units connected together can form very rich abstractions is very meaningful. However, the moment one thinks about the actual scale of the brain, it becomes clear why most people believed that such an aspiration was out of reach. As soon as one seriously considers recreating something inspired by the structure of the brain's neurons, a major problem becomes obvious. We have many neurons in the brain. To be exact, the human brain contains about 86 billion neurons. Roughly 16 billion of those are in the cerebral cortex, the part responsible for higher cognition, reasoning, planning, and abstraction. This is an enormous number, so from the very beginning, it seemed unrealistic to imagine building an artificial neural network with anything even remotely comparable in scale. The gap appeared so large that the aspiration of creating intelligence through neural networks felt out of reach for decades. However, what we are experiencing today is something that almost no one could have realistically predicted. Enough investment was placed into the idea of building very deep and very large neural networks. The foundation of modern deep learning were shaped by Geoffrey Hinton and his team. Ilya Sutskever continued this work for many years and co-founded OpenAI, where the idea of scaling neural networks became a central focus. With Sam Altman leading the organization and with the crucial early investment from Elon Musk and others, OpenAI was able to pursue something that previously seemed impossible: training neural networks at a scale large enough to capture language, knowledge, and reasoning. This was an improbable event, but it happened. And the result of this proof of concept has been the creation of large language models with astonishing and rapidly growing parameter counts across the industry. In the past few years, we have seen a wave of large language models developed across the industry, each pushing the number of parameters to large and larger scales. Not all parameter counts are publicly available, as many companies do not publish exact technical details. However, for a number of major models, reliable estimates can be made. And using these, we can form a reasonable picture of how quickly scale has increased. This chart shows a rough approximation of the parameter growth in several key LLMs over the last years. And the pattern is obvious. Parameter counts have grown at an extraordinary pace from millions to billions, and now will well into trillions. This rapid increase in scale continues today, and it is a central factor behind the dramatic rise in capability that we associate with modern LLMs. The term used to describe this rapid improvement is the neural scaling law. It captures a powerful empirical observation. As you increase key factors in a neural network, including the number of parameters, the size of the training dataset, and the amount of compute, performance continues to improve in a predictable way. In simple terms, if you scale the model, the data, and the compute, the network keeps getting better. What makes this extraordinary is that this trend has held across many different architectures, datasets, and organizations. It has been one of the key forces behind the dramatic rise in the capability of modern LLMs. Although at extremely large scales, some diminishing returns are now being observed, and it is not yet clear how far the curve can be extended or what new architectural innovation might be required to sustain it, the impact of neural scaling has already been profound. It has reshaped our expectations of what neural networks, and especially LLMs, can achieve. To put this into perspective, it's useful to compare the neural scaling law to a previous and similarly empirical trend called the Moore's law. Moore's law observed that the number of transistors on a computer chip doubled roughly every 2 years. That predictable scaling powered the rise of modern computing, personal computers, smartphones, and the internet, and the software industry. It was a major force behind the digital revolution. In a similar way, the neural scaling law has become a driving force in AI. As we scale models, data, and compute, performance continues to improve in a measurable and reliable way. Understanding this scaling behavior is essential because just as Moore's law transformed society through computing, neural scaling is now transforming what intelligent systems can do. Its trajectory is already impacting industry, science, and society, and it is the very foundation that Agentic AI resides on. So let's briefly reflect on what we have discussed. LLMs are essentially very large and very deep neural networks. Because of neural scaling, increasing parameters, data, and compute, these models have now reached a level of abstraction capability that in some ways begins to approach the capacity of the human brain. In the sheer volume of learned relationships and the density of connections they can represent. And that has made them extraordinary abstraction machines. What LLMs are doing at scale is accelerating our movement along the hierarchy, from data to information to knowledge, and towards something that starts to resemble wisdom. The ability to reason, generalize, and act meaningfully in uncertain situations. This hierarchy is what we described as the ultimate goal of intelligence, to extract structure, meaning, and insight from the world. And this is the foundation in which Agentic AI becomes possible. With that, we now have the right foundation to understand how LLMs are capable of remarkable things they do, how abstraction emerges inside these models, how they learn patterns that include logical and irrational structure, and how this forms the basis of intelligent behavior.